Okay, so we left off last time thinking we had two good resonance structures. We said, hey, both of these are possibilities. But in reality, one of these resonance structure is better or more stable, meaning the compound prefers to spend more time in that state than the other one. So our goal is to figure out which one of these is better, either compound 1, resonance structure 1, or resonance structure 2. And to be able to do that, we need to introduce a new concept called formal charge. And the formal charge is the charge an element would have if the electronegativity of the elements were the same. Now what that means is if the electronegativity is the same, we know they want the electrons equally, and that means they would basically share the electrons super evenly. And no one really pull the electrons closer than the other one. Okay, but let's see how this plays out, because this formal charge thing is going to really help us determine which of these resonance structures is better. So when I'm calculating which one is more stable, I want to calculate the formal charge. This is what I'm trying to calculate. I'm trying to calculate the formal charge of each of my elements. Now to get that formal charge, I'm going to need to know two things. The first is the valence electrons of the element. Okay, so how many valence electrons does that element have? For example, I know oxygen, not looking at the compound right now, I know oxygen is in the 16th column. I know it has 6 valence electrons. Carbon, on the other hand, is in the 14th column, so I know it has 4 valence electrons. And this oxygen, well, all oxygens are the same in their elemental phase or stage. And so I know it has 6 valence electrons again. Again, this is just coming from the periodic table. So maybe you want to make a note here. Okay, where did I get that 6? Oh, right, because it's in the 16th column of the periodic table. So the formal charge has to do with the valence electrons. Now, the other thing I need to take into account is something called the electrons assigned to atom. Okay, and this is a little bit trickier. But now I have to actually look at my compound picture. So I'm looking at my compound, and I'm looking at this oxygen right here. Okay, and I'm thinking about how many electrons does this oxygen actually feel like belong to it. Okay, well, it has these 2 electrons next to it. Those certainly belong to it. Those are just electrons right next to it that it has. There are also 2 electrons here, so that's 4 total. Okay, so each electron you see counts as 1 electron. But when you get to the bond, it gets a little bit trickier, because let's zoom in a little bit. In this bond, we know there are 2 electrons here being shared between the O and the C. Now normally the oxygen, being the more electronegative element, would pull those electrons closer, so it would feel closer to having 2. But we're assuming the electronegativity of the elements are the same, which means the C has an equal to pull to the O. Now this is not a great assumption, obviously, because we know the O is better, but we're just going to assume that for now for the purpose of assigning. And so when we have a bond, basically we can assign 1 electron to each of these elements, pretending that, hey, they're equally good at pulling those electrons, and they can actually really only assign 1 of those electrons from the bond. So we have 2, 4 so far, 1 from this bond, but we have 2 bonds here. So we have 1 from this bond, 1 from this bond, 2 electrons plus 2 electrons. That's a total of 6 electrons there. Okay, all right. Now, this carbon here, okay, this carbon, we see it's got 4 bonds around it, and we just talked about how each bond, we can only assign 1 electron from the bond, so I can only assign 1, 2, 3, 4 electrons from it. Okay, and now in this oxygen is the exact same situation as that oxygen. So again, just the 2 from the lone pairs of electrons, and then 1 from each bond, making 6 electrons. And what I'm going to do is I'm going to subtract the electrons assigned from the valence electrons. So I'm just subtracting these. 6 minus 6 is 0, 4 minus 4 is 0, 6 minus 6 is 0. So all of these have a formal charge of 0, and that's a good thing. Generally, elements prefer to have a formal charge equal to 0 if they can. This is a good thing. Elements, it basically means everything's balanced out. It can handle those amount of electrons, and that's why the formal charge is 0. All right, let's take a look at this electron here, and I've accidentally written in the way. So I'm going to move this down a little bit. So I'm just going to move this compound down here. All right, And now let's do the same thing. So again, I'm starting with my valence electrons. I'm just going to say valence electrons here. Okay. And let's go back to black. All right, well, I know nothing here has changed because these are just based on the element. I know oxygen starts with 6 valence electrons. I know carbon starts with 4 valence electrons. And I know oxygen starts with 6. Now, where it gets interesting is the electrons assigned to the atom. So let's think about that. The electrons assigned to the atom. Sorry, this is getting a little bit messy here. But in terms of the electrons assigned to the atom, well, we got 2, 1, 2, 3, 4, 5, 6. And we talked about how each bond we can only give 1. So we've got the 6 plus the 1 here. Well, now that's 7 electrons being assigned to the oxygen. How about this carbon here? This carbon has 1, 2, 3, 4 bonds. We know in each bond only 1 electron from each bond is being assigned. So that's 4. All right, because 1, 2, 3, 4, 1 from each bond. And now this oxygen no longer looks like that oxygen because it has that triple bond. It's got 2 electrons plus 1, 2, 3. That's 5 electrons there. All right, so we just subtract these and we see 6 minus 7, that's -1. 4 minus 4 is 0. And 6 minus 5 is 1. All right, now you'll notice that these have formal charges. There are formal charges on 2 of the 3 elements. And remember we said that elements in general like to have a formal charge of 0. So in this case, we have 1 oxygen with -1, 1 oxygen with 1. Those are the oxygen is a little bit less happy. I mean, it's happy in terms of the octet rule, but in terms of formal charges, it wants to have that 0 charge, and this does not have it. So what we can actually conclude from this is that this element with 0 formal charges is a bit happier than this, which is still relatively okay because it satisfies the octet rule, but does not satisfy the formal charges as well. And so what we actually figure out is that carbon dioxide in general spends most of its time in this resonance structure rather than that resonance structure. So if I wanted to make an argument, I'd write down something like, hey, resonance structure 1 is better than resonance structure 2 because all the formal charges are 0. That means the elements are better capable of handling the electrons that they have. All right, wonderful.